So me and my team, we have been doing some interesting things with machine learning, and that's what I'm here to talk about. About 5 months ago, we updated the WhatTheFont app. And it was a big update. Technology was old, it was using, it wasn't so accurate, and there were user interface issues. You had to tell it which characters or which characters. So it wasn't that easy to use and it wasn't that accurate. So the idea was to replace it with deep learning, which has a lot of power. So that's what we did. And this is an extreme classification problem. My fonts has roughly 133,000 unique fonts, different looking fonts. And the normal ImageNet challenge that the large companies compete in only has 1,000 categories. So it's in a totally different league. And there's some other unique challenges with this, which I will get into. And the bird, by the way, some of you may remember that from last year. That is a visualization of all fonts, the font galaxy into 2D. And that's obviously a multi-dimensional space. And it's projected into 2 dimensions in such a way that it minimizes distance errors between fonts. And that means that fonts that look similar end up in a similar location in this 2D space. And the coloring is another machine, deep learning machine we built, which, given a font, categorizes into a font category. We have 17 categories, so all those categories have a different color. So the WhatTheFont app itself is very simple. You launch the app, you point your camera at something you're interested in, magazine, traffic sign, anything where you're interested in what the font is. The app recognizes the areas where there's text. You pick the text string you're interested in, and it displays the closest matches instantly. And you can also change the text string if you want to something else. And it's available both iOS and Android. And it's just been 5 months. And it's actually been, the reception was very positive. One of my favorite comments in the Apple Store says, "It's so good it feels like cheating." And there's a nice comment here from 9to5 Mac also. And this is superhuman performance. No human could know about 133,000 fonts, but the machine does. So now I want to take a step back and talk a little bit from a high level. What is this AI, machine learning, deep learning business? So AI itself is broader than machine learning. It's more about intelligent behavior by machines. So machine learning itself is a subset of AI. And broadly, there's 3 different types of machine learning. What's called supervised, what's called unsupervised, and then reinforcement learning. And so far, most commercial success has been had with supervised learning. And one interesting thing about machine learning is that we teach the machine by example instead of programming. And supervised means we label the examples with something we want the machine to learn. And the examples actually become the specification, in a sense. And deep learning itself is a specific type of machine learning and it's very powerful. This is on top the traditional software development. Simple steps, you write some code, you compile, you get an executable. Hopefully it works. And you keep repeating that. Deep learning, you collect data, you train, end up with a model. Hopefully the model does something good. If not, you collect data, you train, have a new model. So deep learning and traditional software development are very different. Also, what is deep learning? Why is it not just machine learning? So one key thing is that deep learning has many layers of computation. So it can actually understand more complexity than most simpler forms of machine learning. Actually, more complexity than any other form of machine learning today. One way I think about this is that we have a machine, it's a model, and the data we feed it is the fuel. So to get somewhere, the machine needs enough data, since that's the fuel. If we don't have enough data, we won't get where we want to go. Also, if the machine is too small, not powerful enough, even if we have a lot of data, we won't get there. So we need to have a successful combination of enough data and a machine that is powerful enough to understand the subtleties in the data. And then we are likely to get success. Next, why is deep learning even possible? Why is it we now can do this kind of thing? It turns out, on an abstract level, you need three things. You need what's called a universal approximator, which can map any input to any output. And basically, some of you that remember math, a simple function is y equals a function of x. So you give the function x, out comes a y value. A universal approximator can approximate any function f, no matter what it is. And x, don't think of it as just one value. It can be a long string of values, multi-dimensional values. It can be an image. It can be a sound recording. It can be a font. Next thing we need is, once we have a universal approximator, we need to tune it to make it fit the function we desire to approximate. So we need second parameter fitting. And it so happens there's something called gradient descent, which does this. So that's the second enabler. Third enabler is we need fast hardware. The old CPUs we used to have, or even today's CPUs, are not fast enough. And so people use GPUs, and Google also has TPUs. But both these kinds of hardware can do many simple computations very, very fast at the same time. And this gives us the ability to set the parameters in the universal approximator, which is a deep neural net. Next, I want to share some inspirational quotes that sort of emboldened me to go ahead and do some of these things we've done. This is an old one, 2014, still one of my favorite quotes. I was in Santa Clara in a conference, and Ilya Sutskever gave a talk, and he said that a 10-layer neural network, and by the way, today we routinely build much, much deeper networks. If we have enough labeled training examples, it can solve any problem, or should be able to, most likely, solve any problem that we can solve in 0.1 seconds. With a simple logic that it takes the signal to jump from one neuron to the next 10 milliseconds. So if we can respond in 100 milliseconds, it means signal in our brain jumped only through 10 connections. And this experience told him this was true. And now in 2018, we have many more layers. So what's possible today, it's hard to say. Maybe 1 second of cognition, I don't know. And some of the networks we build today even have memory. So they can see a long sequence of information, and they can start remembering relevant parts of what they have seen. So this one is also a good one from Andrew Ng. And the key difference between this and older ways of doing things is all the ways reach a limit, could not get any better. Deep learning, you feed in more data, it gets better. So that's the unique difference between this and older ways of doing things. Next, a comment from Jeff Dean, heads up Google Brain. Basically, there's good reason to consider using deep neural nets almost everywhere. And if you're not thinking about it, you probably should be. So what can we do with deep learning? It's very simple. We can do better things, or we can do things better. So that's very broad. And we can empower users with better tools that do things that they used to have to do manually. Give more power to users that use our software. And for the business gets value, user gets value, we can gain a competitive edge. So the WhatTheFont AI itself, we show it an image of some letters from some font. It does some computation through its neural nets, and out comes a list of the most likely matches. And one interesting thing is, you've seen this image, there was a background behind the text. So this machine is expected to recognize the text even though there's background elements. There's a gradient, and you see a star around the text. And it was still able to recognize the font. So why is it so difficult? Because this was an interesting journey for me and my team. So I already mentioned we have 133,000 fonts. We have all the letters. We have clean designs. But what this machine sees is, of course, that we have many similar fonts. A lot of fonts look very, very similar. And we only also shown a few letters. There could be some key letters that are very important for differentiating two fonts, but we're not necessarily shown those letters. Also, there are what I call distortions, which is also referred to as a reality gap between what the AI or the deep learning what a neural net sees when I take a picture. If I take a picture of this screen, there's perspective distortions. I'm not exactly in front of the text. The text might be rotated. Could be JPEG compression. The designer could have modified the spacing between the letters. I mean, the machine looks at everything, the black letter shapes, the spacing between the letters. All kinds of things happen to letters. So reality gap, we have very clean designs if you look at them as they are, but what we see, it has a lot of distortions. So that's called a reality gap. So one way to solve that in deep learning is to use a data augmentation pipeline. And we have a very advanced one to deal with the reality gap. So we basically show text from 133,000 fonts to the neural net. But we don't just show normal clean text. We also show rotated text, warped text, text with shadows, with blur, with Gaussian noise, all kinds of interesting distortions. Circular text, gradient colors, just outlines of the font. We changed, embolden the shapes. And one important thing is that we also do when we train the machine is that we sometimes put random images under the text. So if you remember the previous image with a star and the text, so when we train this machine, we have all kinds of natural images sometimes behind the text to teach the machine to pay attention to the text, not what's behind the text. So it was a difficult journey. It seemed really hard. When we started, we had really low accuracy. It didn't work well. It seemed almost impossible. We did a lot of experiments, and we started seeing a gradual climb in accuracy. And after a hard journey, we achieved actually a wonderful accuracy in the end. But we learned a lot. Both me and my team, it was a wonderful learning experience. And our intention is to revisit at some point in the future, make it even better. And next I have a few demos. And so here's the first one. I have a type specimen book. And you see it's clear face, black italic. Point at the text, took a picture. They found the text areas. I click on the italic text right there on the bottom, the italic string, and the results came in. And it found IDC clearface black italic. So that's how it works. And the machine learning part, what's called inference, that processes information, actually lives up in the cloud. Next, another video. Now you see there's an interesting background here. Again, we took a picture. Here the machine did not know exactly what the text is. So manually, we tell it, look here. That's the text I want to look at. And it found the right font. It didn't know what the letters were. And by the way, this machine, we don't have to tell it what the letters are. It doesn't care. But for users, it's nice to be able to type the letters they care about so they can compare the text strings. And you can actually go to my font and look at the font if you want. One more demo. ITC type book, first page, no, cover. Okay, we want that text, collection. And he found the right typeface. So, Stranger Things was actually in a talk, 2 talks back, the Korean talk. And this happens to be the font that they use actually in that TV series on Netflix. So we have done some other font AIs. One is what we call the font attributes. And this reminded me a little bit about the discussion 2 talks back about the spirit of the font. How does it feel? Is it lively? Is it artistic? What story is it telling? The culture. And here we have sort of a random collection of things. I think it's like 31 things we see in fonts, so that we can tell how artistic, how assertive, how attention-grabbing, how attractive, how calm, how casual, and the strange one, how comic book feeling it is, compassionate, how confident it feels, how cool it feels, how decorative, how dramatic, how elegant, how exciting, how feminine, how friendly, how graceful, how happy, how industrial, how legible, how modest it feels, how playful it feels. Does it feel like a poster type of font? Does it feel retro? Does it feel romantic? Does it feel sad, smooth, soft, techno? Does it feel trustworthy? Does it feel youthful? So that's pretty cool. Font similarity is the first machine learning project we did. And the unique thing about that one is that it tells us how similar fonts are, but it's tuned to the same way we perceive similarity as humans. So we showed it hundreds of thousands of examples of 3 fonts, font A, B, and C. And we asked, using Amazon's Mechanical Turk, here's font A. Now look at font B and font C. Which one is more similar to A? Is it font B or font C? And it turns out the machine was able to understand our very human concept of similarity between fonts, or dissimilarity. Another one we've done is font pairing. So this is, I have a font that I like. Now we can ask the machine to show me fonts that pair well with this one. And the last one is font category, which is simply, what category does this font belong to? And it will, there's 17 categories this machine does, and there's humanist, grotesque, and serif styles like Italian old style, French old style, etc. All those basic ones. Questions about fonts, deep learning, AI, any of this? Who has questions? In the middle back.